Hi everyone, this is our project. We explore how to optimize an arc bridge by drilling holes through the structure. We are Group 20. I'm Jiayi.
I'm Xinyu. This picture shows the cross-sectional area of our design bridge. Our bridge has height of 7 meters and total length of 32 meters. The radius of curvature at bottom of our bridge is 10 meters. After we sketch the cross-sectional area, we extrude 6 meters in z direction. Our bridge is made from structural steel, which has density of 7,850 kg per cubic meter. The Young's modulus of steel is 2 times 10 to the 5th megapascal. The tensile yield strength is 250 megapascal. The tensile ultimate strength is 460 megapascal. We use yield strength divided by equivalent stress to calculate factor of safety. For our boundary condition, we apply fixed support at bottom of our bridge, and we apply 10 megapascal pressure on the top surface of our bridge. After apply boundary condition, we use ANSYS workbench to calculate equivalent stress and total deformation. The left-hand side picture shows equivalent stress. The maximum equivalent stress is 74.29 megapascal. The picture on the right-hand side demonstrates the total deformation, which has maximum value of 2.6 megapascal. The maximum total deformation occurs at the center of our bridge.
So we start to optimize this structure. We do optimization by drilling holes through the structure. For the first bridge, we have 9 holes in total, so the maximum equivalent stress is about 87 megapascals, and the maximum total deformation is about 2.9 millimeters. So for the second structure, the number of holes increases, so the maximum equivalent stress increases to 175 megapascals, and the maximum total deformation becomes about 5 millimeters. But the minimum equivalent stress and the minimum total deformation stays nearly constant. As you can see at the bottom right, how the structure deforms. But all four structures deform in a similar pattern. So from the third one to the fourth structure, we increase the number and the size of holes. So the maximum equivalent stress and the maximum total deformation also increase. But from the second structure to the third one, the change pattern is a little weird. We also collect the data for fourth structure in this table. It is very important to note that from the second structure to the third one, the mass decreases, but the maximum equivalent stress and the maximum total deformation decreases. This is because we reduce the number of holes near two necks of this bridge, so at which the maximum equivalent stress usually occur. That's why the condition is a little weird. We come up with a conclusion that in order to minimize the weight of structure at some location where high equivalent stress occur, we should reduce the number of holes or make smaller size of holes. Then at some other locations where low equivalent stress occurs, we should increase the number of holes or make bigger holes. But we should always keep maximum equivalent stress lower than tensile or compressive yield strength in order to reach some safety factor.